You are. Thank you.
Okay, hello, and welcome to our PhD talks. We'll be talking this afternoon, and then tomorrow we've got a few more talks, which will take place in Seminar Room 1 in the Universiteit. Our first talker today is Hugo, and he'll be speaking on computable analysis and game descriptive.
Right. Thank you, Philip. Thank you for giving me this opportunity to talk here. It's very, of course, very nice to talk in this lovely program, and I think it's a really nice idea to have this Leeds Cambridge PhD event. So, as I mentioned in the abstract, this is joint work with Arno Pauli from Clare College, who's also participating in the program, and it's reporting on ongoing work that we have in this. We have a Royal Society exchange grant between Amsterdam and Cambridge, and we've been working on these things. So the background is I'm interested in infinite games and set theory, which I guess most people in this room know have a very well-established tradition. We'll just mention in one sentence, for instance, the Gale-Stewart games and the determinacy axioms, and everybody. It shouldn't be, but okay. And of course, the determinacy axioms and the very rich structure that they have. But today we will not be talking about games for sets, like the Gale-Stewart game, but we'll be talking about games for classes of functions. So the general framework of these games is, well, if the mentality is, well, if you have a function in bare space, then you can think of this as kind of as the task of computing the value of this function at a point as the goal of a player in an infinite two-player game. So we have one player, player one, which we'll think of as male, just so we can talk about him. He's building an element of bare space round by round, so picking x0, x1, x2 natural numbers. And player two at each round responds by playing a move, yn, y0, y1, y2, from a certain set of allowable moves. And then, of course, in the long run, then player one builds an element of bare space x, and player two builds an infinite sequence of moves. And then there's a rule which says which of these infinite sequences of moves are acceptable and which are not. And player two will lose if she plays something unacceptable. But if she plays something acceptable, then the game also tells you what this sequence of move means, right? What is the exact element of bare space that this sequence of moves is encoding. And player two is going to win if the result of this is exactly f of x. And so then when we say that a game characterizes a class of functions, we mean if we have this theorem that a function is in a class that we started with, if and only if player two has a winning strategy in this game. We will see some examples in just a couple of slides, but first let me mention which classes of functions we're going to be focusing on today. So because we have if you have a notion of complexity of sets, then this also induces a notion of complexity of functions. So for example, with the Borel hierarchy, which measures, in a way, the complexity of sets in a topological space, in some topological spaces, we can look at a function and say how complex it is by looking at what it does to the Borel hierarchy. And of course, as usual, the chief notion is what it does on the pre-images, right? What it does on the direct images is not so interesting. So the continuous functions are simple because they don't change any level of the Borel hierarchy on the pre-images, but the bare class 1 functions, which are the pointwise limits of continuous functions, they change the Borel hierarchy a little bit, and so on. And then you can stratify some functions like that. So just to have some notation, we can, given alpha and beta, we can think of the class of functions which the pre-image of a sigma alpha set is a sigma beta set.
Can you just show the previous slide again for the definition?
Yeah, this one. Yeah. So we have a set of moves, a rule, a set of infinite sequences of moves, which is a rule, and then a function which interprets a legal sequence into an element of bare space. Yeah? And these classes go together like this. And today we'll be mostly focusing on this part of the diagram there, but we'll also mention some things about these classes just because there's some interesting examples there as well. So the classical results from like the beginnings of descriptive set theory and functional analysis, the bare class alpha are exactly this functions, right? So if you can obtain a function by alpha iterations of pointwise limits, then you get exactly a function which pulls back an open set into a sigma alpha plus 1 set. So some example of games, of course, the seminal one is the wage game, where the moves are player 2 can play a natural number or she can pass at each round. But the rule is she must play natural numbers infinitely often. And the interpretation function is the obvious one. She plays natural numbers infinitely often, and this is what you interpret as being the infinite sequence of natural numbers. And this characterizes exactly the continuous functions. We have the eraser game, which is usually attributed to Dupac, but I guess it might be just folklore. That if you add a new kind of move that player 2 can make, so you do the same as the wage game, but now she also is allowed to erase a past move. The condition being, well, she must play natural numbers infinitely often as before, and she can only erase each position of her output finitely often. And this gives you back class 1, or lambda 1, 2. And if you allow her to erase past moves in a more dramatic way, she erases everything that she's done and starts over, and you only allow her to do this finitely often, then you get exactly lambda 2, 2. So the preimage of sigma 2 sets are sigma 2 sets, and this is due to a lot of people, I guess.
So in the eraser game, you mean you're allowed to erase just the last move or some other previous move?
Yeah, you can allow, let's say, an arbitrary previous move, but each position of the output can only be done, can only be erased finitely often.
And then at some later step, you can play.
You play something else there. Yeah, you replace a past move with a new number.
And the next number you play will be replaced in the least gap that you have when you
Say that works. Yeah,
Okay.
that will work. And the backtrack game gives you lambda 2, 2, and this uses very heavily the Jane-Rogers theorem. Yeah.
What is player 2's aim?
Player 2 wants to make sure that whatever sequence she plays gets interpreted as f of x, where x is what player 1 is playing.
Okay, and how does player 1 win?
If he can make sure that player 2 fails at doing this.
But so player 2, the set of rules is just a subset of the bare space.
You have a set n.
Yeah, so it depends how exactly you want to implement this. For example, if passing is an actual move, then this is, right, you take something that's not a natural number and this is interpreted as passing. So then the set of rules is the sequences of natural numbers or passes.
Okay.
And then interpretation is erase all passes.
But so that's why you had this interpretation thing which actually can convert a subset of the bare space into what actually the output would be, where you can sort
Yeah,
of
but it's not necessarily, doesn't necessarily come from a subset of bare space. Actually, the next example is going to really. So Brian Sams in early 2000s, I guess, in his PhD thesis introduced a few other games which are kind of significantly different. So at each round, now player 2, instead of playing a natural number, she plays a finite tree. And not only that, but she plays a function associating to each node of the tree one natural number, except for the root, because we don't care about the root of the tree. And the rules are, well, she must always extend what she has done before, so she cannot erase a node of a tree that she has already played. She can only add new nodes. And she cannot change the labels of the nodes that she had already played before. She can only play new nodes with new labels. And then the infinitary part of the rule is that she must be, this tree that she's building in the long run, right? So the union of all these trees must be a tree with one infinite branch. And then the interpretation function is, well, take this infinite branch and look at the labels along it, right? This gives you an infinite sequence of natural numbers. And then Brian's theorem is that this characterizes exactly the Borel measurable functions. So those functions which, if a set is somewhere in the Borel hierarchy, then the preimage is somewhere in the Borel hierarchy. And by restricting this, Brian was able to characterize some subclasses. So for characterizing lambda 1, 3, you need to add one extra rule to this game, saying that this finite tree that she's converging towards must be finitely branching everywhere, except possibly on the nodes which are on the infinite branch. So if a node is on the infinite branch, it is allowed to have infinitely many children. If it's not on the infinite branch, then it cannot. And this gives you bare class 2. The lambda 2, 3 class is you must be finitely branching everywhere on the tree except possibly the root. And the 3-3 is you must be linear, meaning no, just exactly one children everywhere except possibly the root. Okay, so our goal here is to kind of make this a little bit more uniform, let's say, and to kind of understand what is going on in the background, so to speak. So we're going to try to isolate where exactly the complexity of the class occurs in the structure of the game. And for this, we're going to need to be a bit more general. So I'm going to need to introduce some things from computable analysis and Weyrauch degree theory. It's not too much, but so we're going to be talking about multi-valued functions, which is, strictly speaking, just binary relations. But it's really helpful to think of these as non-deterministic operations. So in particular, the different values that f of x can be, we don't have any preference between them. And with this mentality, we see that composition of these things is not exactly relational composition, because, well, actually the value, so if the values that are in G after f of x are, well, exactly the things that you can obtain by first doing f and doing G as before, as usual, but the domain is different. Whereas in the relational composition, you would have an existential quantifier here, right? Anything that some way that you can do the two-step is valid. Here, the first step must always give you something which allows you to take the second step. So that's where this universal quantifier here is coming into play. And this makes the multi-valued function composition different from relational composition. And with this mentality of no preference over different values, we also see that the kind of correct notion of extension of function is this thing called tightening. So f tightens G if, well, the domain is larger, as expected. And anything that you can do with G, anything that is a valid input for G, so it's also valid for F, any possible outcome for F was also possible for G, right? So maybe you don't get all possible things that you could get from G, but you get some. And because we don't care about the different values, this is enough. So in particular, if you want to know G, it is enough to know F, if F tightens G. And this will play a role in the rest of the talk. This is the chief notion of being good enough. And we're going to be talking about things that are not necessarily bare space. So we will, in general, be talking about represented spaces, which are just sets with surjections from bare space. So for example, later on, we will be talking about the represented spaces of trees. And if you have a function between represented spaces, then we can talk about a function in bare space being a simulation or realizing this function, meaning that it makes this diagram commute. And what I mean by commuting is going right and down is a tightening of going down and right? So anything that allows you to go down and right will also allow you to go right and down. And the value that you obtain by going right and down is a member of the set that you would obtain from going down and right. And because we have very many notions for functions in bare space, we can now extend these represented spaces by just saying a function between represented spaces is continuous, for example, if it has a continuous realizer or a computable or so on. And I guess the main tool for comparing these kinds of functions between general represented spaces is Weyrauch reducibility. So if I have two multi-valued functions f and g between general represented spaces, we'll say that f is strongly Weyrauch reducible to g if there's two computable continuous functions, inputs and outputs, just to keep the mnemonic, say, such that if you plug in between them a realizer for g, then the resulting composition is a realizer for f. Right? So the things that simulate f can be uniformly obtained from the things that simulate g. And this is strong, as the name says, because this is kind of too fine. So for example, with this, you can differentiate the strength of the identity function and any constant function. So this is really fine. And this is kind of too fine in general for what we want to do. So we have the non-strong version of byte reducibility, where we feed, so it's exactly the same except that the output function also has access to what the original input was. And this gives us kind of the correct granularity. So we have these two notions of reducibility, but we will be talking today about things where this difference doesn't matter. So a multi-valued function is going to be called a cylinder if being Weitauf reducible to this function is the same as being strongly Weitauf reducible to it. This means that f is exactly Weitauf equivalent to the identity times f. And we're going to be talking about functions which are transparent in the sense that whatever continuous function you want to post-compose with your f, there is already a continuous function that you can pre-compose with your f, which gives a tighter result. So you can kind of push continuous functions through your f. And if you have the conjunction of these two properties, then this behaves well with composition, because if f and g are transparent cylinders, then so is their composition. And this will be important later for us. And we don't lose too much by demanding these things, because Vasco Bratka and Arno have shown that in any Weitauf degree, you always have at least one representative with these two properties. Okay, and so transparent cylinders will be important for us because they will be the main thing that captures the complexity of a game. But we will also need something kind of playing the role of an interpretation function. These are called probes. So a probe for a represented space Y is just a continuous function or partial continuous function from Y into bare space, which has a certain universality property. So any other function that is continuous from Y to bare space can be obtained by you first transform your space Y continuously, and then you apply your probe, and you get a tighter result. Okay, and then with these two ingredients, we have our pi t wage game. Now comes a bit of an ugly diagram, but the point is, if t is, well, okay, if t is just a function from between represented spaces, and you have a probe for the codomain, then you can define this game. You are given a general function between represented spaces, and player one builds something which is a name for an element little a here in the domain. If it's not in the domain, then we can say that player one loses. And player two has the task of, by looking at prefixes of this name that player one is building, she must build a name for something in X. That's it. And what she must guarantee is that if in any way that you have of applying t to this thing that she's naming, and then applying the probe, you get something which is a name for something in f of a. Yes?
Maybe give an example of it.
Yeah, we will. Yeah, we'll see some just in a minute. So just for let's say sanity check, the wage game is the identity. So this whole thing kind of collapses, and then we just have bare space here. Sorry, and then a continuous function between bare space, and then the wage game theorem just says that this works. The eraser game is, well, the probe is again the identity, and the complexity is captured by lim, right? That's where this condition of erasing each position finitely often comes in. This is exactly saying that you are in the domain of lim. And the backtrack game is the discrete limit, right? So you're building a sequence which changes finitely often and then stabilizes, right? That's exactly discrete limit.
In the eraser game, what is X and what is Y?
Bare space.
Both of them are bare space.
In all of these.
Okay, and what do you mean by lim?
Well, so let's say it's infinite sequences in bare space, which is just bare space, right? So you take an element of bare space, and then via some suitable coding, you see this as coding infinitely many elements in bare space. And then lim is just the limit of these sequences, point-wise, coordinate-wise. And lim delta is the same, except that in order to converge, the whole sequence must be stabilized at some point, not point-wise. Okay, so for these three simpler games, we can see them in this framework. And the problem is, well, how are we going to see Brian Sams's theorem games in this framework? But that's the second part of the talk. But first, the main theorem that we have in this general setting is, well, if the T that you started with was a transparent cylinder, then for any probe pi, the being reducible to T is exactly the same as player 2 having a winning strategy in this general game. And that's why we get the three theorems that we had before. So just combining this with Vasco, Bratkas, and Arno's theorem, in every Weidauch degree, you have a T with this game property. Okay, so we now want to see Brian's theorems in this setting. So we're going to need first to observe that there's a certain notion of equivalence going on in the background of the trees, because if you imagine a run of the tree game in which player 1 builds some X and player 2 is building this labeled tree on the left. Now another run where player 1 is again building X, but player 2 is building this tree on the right. Right? It's a labeled tree, right? So the fact that it's a 0 there just means that the label is 0. The actual sequence is something different. Right? Doesn't matter what. Right? These are different trees. But the point is that the tree on the left is going to be a win for player 2 if and only if the tree on the right is, because the things that matter are the labels on the infinite path and whether or not the tree has a structure that is legal. So these are really the same. So we're going to have to quotient these things out by some equivalence relation. And it turns out that the equivalence relation that we need is bisimilarity. So from computer science, let's say. So two label trees are bisimilar if you have some binary relation between them, which relates the roots. And whenever it relates a sigma from one tree with a tau from the other, then sigma and tau have the same length and the same label. And you have the forth and back conditions. So forth says any way of extending extending sigma in T, for any such way, there is some way of extending tau in the other tree, and you get bisimilar nodes. And vice versa. Any way of extending tau corresponds to some way of extending sigma bisimilar. And as I indicated, we're going to be working with quotients of trees under this relation. So let's say an abstract label tree is just an equivalence class of label trees under bisimilarity. And of course now an abstract label tree is no longer a tree itself, right? Just a set of trees with some property. But I'm just making an informal comment here. We can think of these as trees which have no order, which have no underlying set of vertices, if you think of them co-inductively. So if you think that in order to specify what a bisimilar tree is, what an abstract tree is, what you should do is specify one natural number, which is going to correspond to the label at the root of the tree, and you're going to specify a countable set of abstract trees, which are going to correspond to the trees which exist here below the root. Right, and this is co-inductive, so now you have to specify each of these, and this goes on. Of course, this won't really work in ZFC, because if you have an infinite path, then this would be an infinite descending membership chain, right? So but this can be made to work pretty well in non-well-founded set theory, say AFA, right? So Axel, I guess Hansel and Forte use. So where you take away the axial foundation and you add a corresponding nice notion of which non-well-founded sets are allowed. And this works pretty well, but I won't get into it. But I think it is helpful to have this picture in mind, that an abstract tree, although it is just an equivalence class of trees, can itself be seen as a tree. Okay, and then we need to code these things, right, in order to get a represented space. I won't bore you with the details of how to actually say what a code, so what an an element of bare space, how it codes trees. The only thing that really matters is that what turns out to happen is that, so we have an abstract tree, which is a set of concrete, of actual label trees. And it turns out that each label tree corresponds to a different name for this abstract tree. And we're going to be talking about properties of trees, which we have for actual trees. So we need to extend these to abstract trees. So we need to say what it means for an abstract tree to be finitely branching or whatever, or finitely branching outside of the root and so on. And we can do this just by saying an abstract tree has a property if one of its representatives does. Now this doesn't really work so well intuitively, right? Because let's say this tree, whatever labels, just 0, let's say, this is bisimilar to this tree. There's zeros everywhere. Right? This is a finitely branching tree, this is not. But they are bisimilar. So in the equivalence class, the corresponding abstract tree is finitely branching, even though some representatives are not. But this doesn't break much. And so then we get some subspaces of abstract trees. For example, the space of finitely branching abstract trees. Or the ones that come from trees which are like this, linear infinite height trees. So these are the proper prunes, right? Just to have some name. Proper pruned abstract trees, which are trees in which they have infinite height and only one label is allowed to happen at each level. So these are exactly the abstract trees which have a representative like this. Okay, and then we get one example of a probe. The operation which receives an abstract tree bisimilar to one of these, and the task is, okay, output the labels along the infinite path. Right? It doesn't really matter if you get this tree or this tree. If your task is to spit out the unique infinite label that occurs, right, level by level, this is computable, or we're just talking about continuous. So this is continuous, and this is universal in that sense, because if you have a continuous function going on here, then you can change your input tree correspondingly, so that the label, the infinite label, now has that value the transformed value. So this is a probe, and this will be the probe in the game. And now we just need the corresponding complexity transformation. And this is going to come from this pruning derivative. So if you're given a tree, let's say an actual just classical tree, you can think of a certain derivative as, well, just go to your tree and see which nodes are roots of trees with infinite height. And keep those and throw away everything else. So just, and for example, anything that is on an infinite path is going to survive this operation. Things which are not on the infinite path may survive this operation. For example, that the node on top there, the one with the infinite branching, is going to survive, because even though it's not on an infinite branch, it sees infinite depths, it sees arbitrarily long sequences below it. So if I derive once, then I get this tree. And then if I derive again, I get this tree, of course. And so this works on trees, but it's not hard to see that if you start with 2 bisimilar trees and you do this operation, then you get again bisimilar trees. So this is also an operation on these abstract trees. And the main thing going on here is, well, this is a transparent cylinder. So this is going to work well for our game. And this has the exact Weidhoff complexity of 2 limbs. So maybe I have 15 minutes according to, maybe there's some time to do a sketch of this proof. So the complexity, the fact that with 2 uses of lim, you can compute this operation, works out because, let's see how precise do I want to be. You will use 1 lim you will use 1 lim to so you were reading the code of a certain tree. Right, you're reading this, let's say, in omega many stages. So one of the limbs is going to take care of the stages. And so at a certain stage, you have certain nodes that you've put already in your tree. And you're going to take care to see at this stage which ones already see a certain depth below them or a certain height above them. And you're going to just, it's tedious to see how to actually encode this using the continuous function in that you're going to do. But the point is that you can do this in such a way that you have control over at stage n of the tree. These nodes already see depth m below them. And then the 2 limits that you're going to do afterwards, because you've encoded things in the correct way, one of the limbs is going to take care of going through all the stages, and the other limb is going to take care of going through all the heights. So the only things that survive these 2 operations are exactly those nodes which see infinite height below them. And it's kind of, I won't bore you with the details of how to actually encode this using a continuous function, but it's all finitary stuff going on, right? So you're just looking at a certain prefix of the code of the tree, and with this you already get a finite little tree, and then there you can see how the heights are working, and this works. And then you get this direction. For the other direction, you should think about that this condition you can express, right? So this is right. So we're trying to find these values for these values. So this has this certain shape like this. So this happens if and only if there is a certain point in the sequence such that at all later points there is again some point of the sequence such that for all later points, and then something happens. I guess maybe the order is right. So it's something like this. And the idea is, I really don't have time to give you many details, but you can put these things in a tree in a way that playing a certain node at height n here, you are going to encode a guess for k, and you're going to encode a guess for n0. You're saying the value is going to be 17, and the corresponding n0 is 105, and you're only going to, and all descendants of this guy are going to help you verify that guess or not by providing the corresponding n1, where the difference in heights here is exactly n0. So you play a node here. This node is at distance n from the root, so it must make a guess for what k is. It must make this guess and the corresponding existential quantifier here. Now, you're only going to, and the task of verifying these guesses is going to be left for the descendants. So a descendant at extra height n0, so n plus n0 here. is going to have to also encode somehow a guess for this quantifier. And then it is guessing that for all n1s, this thing works. Oh yeah, sorry, yes. Right? So the point is that you can make it so that you're only allowed to place something here if both of these guesses are correct. So this guess and this guess are correct for these two values. And then what happens is, if you do this in the right way, the nodes which are wrong, the nodes which make wrong guesses, only have a certain finite depth below them. And then they die when you do one derivative. And the things that survive are exactly the ones which have the right guess. So using one derivative, you compute two limits. Okay, and that's that for the complexity. And for the fact that it's a cylinder is not super interesting, but the fact that it's transparent is also, at least I consider, kind of interesting, right? So the point is, so
could you remind us what
yeah.
transparent means?
So you have this you have this space, and you have this operation. And the claim is whatever continuous function you want to do here, there was actually already a continuous function that you could have done here. Such that if you do that first and then you derive, then you get something this way which tightens what you would have done this way. And the thing here is that f is continuous, meaning it has a continuous realizer, right? So a function in actual Baire space, which works on the names of these things and simulates this. And this is continuous. So by the wage theorem, this has this finitary dependence thing, right? So we know that we're trying to guess what the eventual output is going to be. And because this guy is continuous, we know that we're going to put a certain sequence there with a certain set of labels, sequence of labels, if in the input one of countably many finite little trees occurs. Right? These are the things which trigger your f to put this thing in the output tree. So what we're going to do here in this transformation is we're going to build a tree which, once you see this thing in the input, let's give these things names. Right, so recall, these are the finite pieces of the input tree which cause your capital F to put this tree in the output. So once we see one of these, we're going to add this to our tree. But we're going to do an association. I'm putting this thing here because of this. Right, so this is going to be encoded. This information is going to be encoded by this node here somehow. Now the thing is, this must exist in the derivative, right? It already exists in the input, but the thing is, I'm guessing it's going to survive a derivative. Meaning it's also going to be here, so that this actually occurs. So I'm going to have to keep track of whether or not this thing survives a derivative. So in the input tree, this thing already exists, but it may still die. So the point is, I'm going to, once everything in this tree sees a depth n below it, right? So this thing is extended n, then I'm going to allow myself to extend this guy n. Only then. So if at some point these one node here fails to be extended to depth n below it, I'm also going to stop this. So if this thing survives the derivative, then I'm going to, I mean, I'm throwing some details under the bus here, but under the carpet here, but then this thing is also going to survive. And then you can do this in a way that works. But here is where the whole bisimilarity thing comes into play. Because this thing is attached to this witness. But it may be the case that another witness also survives, also exists and survives. And then we're going to get another node here. But we can do this in such a way that I know that if this happens, then whatever happens below here is actually bisimilar to what happens here. And this is where the whole bisimilarity mechanism comes into play, because we can kind of relax. We don't need to keep track of doing just a unique thing, and we can repeat things in such a way that doesn't harm. And you just argue that this works out. Okay, right. So that was the main theorem, and then just putting this together with some results from the literature. I guess this is usually attributed to Bratka, but it might be more folklore. Is that, well, the nth composition of the limit operation is Weierach complete for Baire class n. And then putting this together with what you just saw, if you take the nth composite of derivative, this is equivalent to 2n composites of lim. And then if you restrict this to those trees where if you do n derivatives, you get a linear tree, a proper prune tree, then this game characterizes exactly Baire class 2n. Just translating this back to a language that we have from the beginning, if you take Brian's tree game and you restrict, you add a new rule saying the resulting tree must be such that the nth derivative is linear, then you get a game which characterizes Baire class 2n. Right. And then in order to get 2n plus 1, we have to do something a little bit more subtle, right? Because adding, by this theorem, if we add one more derivative, then we get to 2n plus 2. So we need something in the middle, and this is very much related to finitely branching. So if you restrict the tree derivative to finitely branching trees whose derivative is proper pruned, right? This is an actual restriction, right? Because you have non-finitely branching trees whose derivative is pruned. So this is an actual restriction. Then you need to reprove your theorems from before, and you get something that is equivalent to lim, and which is a transparent cylinder, right? So you have to argue that in this construction, you don't. If you started from a code of a finitely branching tree, then you also, this transformation is again finitely branching. This is not trivial, but this works. Then you just do this new special operation after you did n composites of the previous operation, and you get exactly 2n plus 1. So in other words, just back to the tree game, if you take the tree game and you add the rule that the nth derivative of the tree must be a finitely branching tree, then you get exactly a game which characterizes Baire class 2n plus 1. And as I mentioned, this is ongoing work, so we're moving towards a transfinite, and we also should see about what happens, right? So these are just the lambda 1 alpha classes, what happens with the alpha beta general. And so this is part of our project. And thanks very much for your attention.